Okay, so this week there is no lab, and of course I still have things running in the background. There is no lab, but we still have topics to cover, and the project will go over that as well. Stuff. Yeah. Okay, so yeah, we're going over sorting, searching, and time complexity on the project. So to start us off, sorting, searching, time complexity. We're going to go over the sorting algorithms you need to know first. There are 3 of them. Obviously, there's like a billion of them, but there are 3 of them we're going to go over. To assist with that, we're going to have little video sorting algorithms. I like this one. It's an oldie but a goodie. So the 3, just for terminology, I think we've already covered them in the lecture. So I'm literally using like the lecture slides as an overview. But it's insertion sort, selection sort, and bubble sort. So if someone came to me and said, what is insertion sort, what is selection sort, I could not 100% tell them which is which. I know both of them. I know I could tell you what both of them were, but I could not assign one name for one of them because they're very similar, just in my head, reverse concepts. But you guys have to memorize it. So right here is selection sort. The way selection sort works is that there is unsorted data, and you can see it's going through all the unsorted data every single time. So that this red is saying what it's currently looking at, because the program can only do one thing at a time. And so it's looking at each piece of unsorted data, finding the smallest, and then putting it at the end of a sorted section of data. So in this case, smallest, the sorted section of data, and you keep doing that forever, you'll eventually get the largest and put that at the end. And so all of your stuff is complete, completely sorted. So that one is selection sort. See right here too. I'm going to do insertion sort next. Insertion sort in my head is kind of the opposite. It takes the next element of the unsorted section. So you see here, we're not going through all the elements of the unsorted section. And then it inserts it into the sorted area at the correct place. So here, sorted area, you'll see that it's going through a lot of the elements. It's not always going through all of them, but it's going through a lot of them. And placing the next element in the right place. In general, insertion sort is faster than selection sort because selection has to go through all the unsorted data every single time. But insertion sort, it might be able to place it at the beginning very quickly. So just in general, you don't need to make this sort. But just in general, insertion sort is more efficient. But both of them, when we get to time complexity, at the same time complexity. So we'll cover that later. But yeah, that's insertion versus selection sort. And bubble sort, look for the thick. Yeah, here we go. So the way bubble sort works is that it constantly, when I pause it here, it's got a lot of red there, but that's just because the frame rate has it looking at a lot of pieces of information at once. But bubble sort, what it does is it checks 2 elements at a time, and if they are in the wrong order, it switches them. So that's what that does, and then it keeps moving along one by one. And what this ends up doing is that specifically for data that's going from smallest to largest, and if you're looking from left to right, whenever it finds the biggest data and the information, it drags it all the way to where it's supposed to be. We'll see that here with it's dragging the biggest information, because if it finds the biggest one, it's going to keep swapping it until the end. Just the other small side effect is that the area where it's technically still unsorted progressively gets more and more sorted. So, as you can see, it's unmuted. How dare you? Oh, you muted yourself. But so yeah, just the area that's unsorted does sometimes you can think about it if the largest one is at near the end, all that switching does help the sorting part as it moves along. So it does help that, but in general, bubble sort, it moves the largest one to the end, just with a little bit of extra help in between as it's swapping. But so yeah, those are the three that you need to know. They are definitely the basic three sorting algorithms, like the first person who decided how to sort something when they're just like talking about it. It's very easy to conceptualize these sorting algorithms. There are some really wacky ones. Most of the wacky ones involve some sort of breaking up the data. And so here, this is, standard sort, I think uses radix sort, yeah. So radix sort, it breaks, it says, it scans all the information first, finds the range of values, and then sorts it into chunks of sorted information. So, but again, you don't need to know that. There's definitely just more efficient ones than what you've got right here. So you guys just need to know these three. And we'll go over implementation, but just conceptually, does anyone have any questions on these three? Okay. Then the searching ones, you have a very basic one called sequential search. I call it linear search. So there's no thing for that. Linear search just starts at the beginning of the data and goes until the end of it, looking for what you're searching for. The worst case scenario is that the thing you're looking for isn't in there, so it has to check all the elements. The best case scenario is that it's at the very beginning. So you just have to check one. Sequential search does not require a sorted set of information because it's just going from left to right, doesn't care if it's pre-sorted or not. Binary search does require that the information is sorted. So this does require sorting it first, but then using this is much faster. The binary search works, assuming that the information is sorted, it checks the middle element, and then by whatever you sort it by, if what you're looking for is less than that middle element, then it checks only the less than element. So it basically can cut off half the elements. You don't need those anymore. And then the reverse, if what you're looking for is greater than that middle element, then it just goes to the greater than section. So however you sorted your information, that's how that works. In general, if you're like, is it more efficient to sort and then do binary search or just do a linear search? In the field, if the thing you're searching for, you only have to do it once, a linear search, a sequential search is fine. Sequential search would do what you needed to do. However, most of the time when you're searching, it's through a set of data that you're going to be searching lots, like you're searching for multiple things over multiple times. And so it's a good idea to just sort it first and then maintain the sorting this sorted component of it so that you just can use binary search much faster. Yeah, those are the two searching algorithms you need to know. Concept. So we'll cover the like implementation of it again later, like I said, but any questions on concept? Okay. So now we get into like the bread and butter of this unit. So searching algorithms and sorting algorithms, those are great to know. Just if you're working on something, you know what you need to implement. But honestly, most programming languages have something built in. Like even here in this thing that it was showing, yeah, this thing is called std sort, the sorting algorithm. It's called std sort. And what that means is that this is the sorting algorithm that's built into C++. So most languages have a built-in sorting algorithm that is very efficient. You just give them what you're comparing, what number you're comparing, and it sorts all your information for you very quickly. So yeah, most of the time you don't actually have to implement a sorting or searching algorithm, except we will be implementing a searching one later for this class. That's because we tell you to. But just in the field, you don't have to. But it's good to know what they are and what their time complexity is so that you can choose the best one for the job and then just look up the implementation. But you do actually need to know the time complexity. So the first basic component of time complexity in computer science is called big O notation. You'll learn about more types of notation because obviously after I explain this, you're going to be like, well, that's kind of, there are some cases where this is fairly useless, not useless, but not, it's, big O notation is important for if the amount of information is going to scale. So if you're thinking about using a large amount of data, so if you just have like billions of data points, you want something that has a low big O notation. You'll see why in a second. So the way big O notation works is that it usually has a variable n. So like here we have like O of 1, O of n, O of n squared, O of log n, and yeah, so there's those. There's definitely more than that, and I'll show you a second in the graphing calculator. But what those notations mean is that your equation, if you graphed it as like x is the number of elements in your data set and y is the time, it would look like what you put in here. So if something has a big O of 1, that means it looks like a flat curve. Like there's no actual curve component to it. O of n looks like a linear, just straight line. N squared, it looks like a quadratic function. Log n looks like a logarithmic function. So if we go to a graphing calculator, and we just do y equals 1, y equals x, y equals x squared, and then y equals log x, like that. Those are the three big ones you guys really need to know at this point. Based upon log x, you should also be able to identify an x cubed, and we'll talk about how to identify it in a second. But just any polynomial, really, you should be able to identify. Technically, some of the other ones that exist that we'll cover later are like exponential, so like 2 to the x. Also factorial. So in the future, you'll have to be able to recognize these, but that's just more advanced notation. So right now, we're just going to look at these three. So with these three, just looking at it, you can see what those curves look like. And all we care about is just what they look like and generally how they move. So this x cubed thing is definitely the steepest. Log x is the second lowest because the y of 1 is the lowest. It's below that too. X squared is right there, and then y equals x. And you really need to know which one increases faster, because that's important when you're actually figuring out what the big O notation is. So you definitely need to memorize. Hopefully it's not super hard. The weirdest one might be log of x if you're confused with what that looks like, but when you see log of n, that's really low. That's really good. The only thing better is just a constant. So with this, if you have an equation where it's like, if you have a algorithm that's just 1,000 lines of code, but there's no loops or anything in that, like it's not based on any data set, it is just 1,000 lines of print statement or something, technically it would take 1,000 commands to run. So you could say the time complexity is 1,000 commands. And so while that has a really high amount of time that it takes, its big O notation is 100. It's O is 1. It is O of 1. That's because it never changes based upon the data set you're using. If it's a linear one, so maybe it's something that is a loop and it runs based just n number of times, but it has 100 calculations per loop, so you like 100x, you'll see that this is a very steep curve. Let's do like 20. Get 20. There we go. So like down here, 30x is very steep. So you might be thinking, oh, that's super steep. That's the highest, that's the steepest curve. Except when you get up here, slowly and slowly, x cubed, x squared, that is faster. So that's why the cubed and squared part are faster. And so if you have something that is linear, no matter what the constant in front of it is, its big O is O of n. And so yeah, same thing with x squared, x cubed. Log of x is a little harder to tell when it is, but anytime when the data set gets divided by like 2, 3, anytime it gets cut into chunks, it's usually a log big O. That's what you're looking for. Because log is saying, inherently log is base 10, but log is saying what value it's like what value of exponent does this make, what value of exponent does the base need to get to x? And so if it's log of 10, then the answer is 1. If it's log of 100, it's 2, 1,000, it's 3, 10,004. So it keeps multiplying by 10 to get there. But if it was like log base 2, if x was 2 would be 1, 4, 2, 8, 3, 16, 4, so on and so forth. So that multiplication factor. So to get a higher time, you have to multiply the data set by 2. You have to multiply the data set by some constant, and so that's what makes log of x, is that it doesn't, the time increase does not happen very quickly. You have to drastically increase the data set to get a larger time. And that's what you're looking for. You want your time flex to be really low no matter what. You want the amount of time your program takes to run to be really low no matter the size of your data. So just anytime you see multiplication, there's a chance that's log x. Obviously, it might not be. We like to give you trick questions so people look out, but that's what you're looking for that. So conceptually, that's what big O is, time complexity. Based on the sorting and searching algorithms we talked about, all of the sorting algorithms have a time complexity of n squared. A big O of n squared. It's because they have to check, the amount of information you have to check is the number of elements, the number of elements times. So like if they're going through all the data, they have to do it, if there was 6 elements, they'd have to check through all the elements 6 times. Now, technically, you might be thinking for like selection sort, it goes into the sorted area, so it doesn't cut down the size it has to search every single time, but it's doing that in a linear fashion. It takes off 1 every time. If it was taking off half the elements every time, that'd be different, but it's taking off just 1. So that's a linear cutting of information. So like if we look Excel, with a selection sort, if there was 1 element, it would just have to check 1 thing, it's already sorted. If there were 2, then it would have to check both of them to see which one's the lowest one. And then check the last one just to make sure it's sorted. So that'd be 3. If there were 3 elements, it'd have to check 3. So basically it keeps adding. So this would be 6. So that's check all of them, then 2 of them, then 1 of them. And so on and so forth. If you keep doing this, 10. Each element you add to the unsorted set, it has to check that plus the previous one's amount of elements. And if we graph this, might be really small, by the way. If you graph this, and then find the line of best fit, it's gonna be a polynomial base 2, and just the equation. The equation is very easily 0.5x squared plus 0.5x. This minus 4e to negative 14, that's basically 0. So yeah, we add a little 0, 0 here and increase that. That should fix. Oh no, it's still being weird. But this little constant here is a 0. This 0.5x does exist, but the main thing we're looking right here is this 0.5x squared. You only take the biggest component of it because if there was the biggest component dictates what the actual curve looks like when there's a ton of elements. So if there's like a billion elements, this 0.5x would barely even factor in. This x squared would be huge. So that's why we look at that only. And even though there's a constant in front of it, we don't care about that. Just like we saw for the 30x squared, it eventually looks like just an x squared function. So selection sort, x squared, the same property applies to insertion sort, except insertion sort, like I said, it does check less and less, but it's still, in the worst case scenario, it works exactly like selection sort. In the best case scenario, it might be a little bit faster, but on average, it's somewhere in between selection sort and n. So that means it's like 1.2 n squared is like the average. But again, it's still n squared, so it's O of n. And then bubble sort. This one is different than the other two, but again, still n squared. It goes through all the elements n squared times. Similar reasoning from selection sort. So yeah, all your sorts are n squared, so don't worry about that. There are definitely sorts that are not n squared, like the ones we were looking at where it breaks up the data. Did I close it? Oh no, yeah, so the ones that are like breaks up the data into chunks, there's a logarithmic component in there somewhere. The fact that it's breaking up into chunks, like I said, that's what you'd be looking for log. Your searches are definitely more efficient. Sequential search, big O of n. It's just checking all the elements. Worst case scenario is all of them. Best case scenario is 1. The average is like 0.5, but again, it's 0.5 n. So it's just n, big O of n. Binary search, this one is breaking it up into chunks. So it's checking the middle. If it's greater than the middle, less than the middle, it goes to either greater than or less than side, and it cuts off half the elements. So binary search has a big O of log n. Best case scenario, it checks one element. Worst case scenario, it has to check log elements. So like, let's say there's a log, well, binary search would be log 2. Yeah, it'd be log base 2 elements, but any base, so log base 2, log base 3, 4, 5, whatever, it's still just log. Same reason why x squared, 50x squared is the same as x. But so if there was this 7 elements, the max S check is 1, 2, 3. Yeah. And that's about log 2 of 8. So yeah, it's log base 2 of 7 would be near 3. Yeah, log of n. Cool. So that's the time complexity, the ones that you're given. You definitely have to just memorize that unless you want to. We talked through like why it is. So you can remember that as well, but you do need to just know that. We should be able to ask you what's the time complexity, the big O time complexity of binary search. You should be able to say that then. But you should also be able to look at an algorithm and tell us what the time complexity is. So anything that's just like a flat existence, so like just a single line of code, like a printout statement or return true, that would have, like when you're writing out your equation, you would say that that has a big O of 1. If statement's also big O of 1, but then here's this for loop. That's a big O of, so num.length, num is an array. So that'd be a big O of n. It goes into it further, right? No. Okay, so this one doesn't have the solution here for, but that's fine. I know I'm right. So this one has a big O of n because this for loop goes through all the elements of num. Now it does these operations to it, so that's it does 2 operations per element. So it is, you might be able to think if you're just writing out a base equation, it would be 2n. But again, cut off the decimal place, so the big O notation is O of n. O1, 2, and for the log. Yep. Just generally, so we're about to go into some coding examples, but as you're thinking about it, you ignore lower order terms. So if your equation ended up being something like n squared plus 10, even like 1000n plus 5, it's still big O of n squared. Even though the n is bigger, big O of n squared. Because if you have a data set of 1 billion, like I said, if you think about it as 1 billion, n squared is much bigger. So that's going to dictate what the curve looks like, even though this 1000n will make it take a long time. Ignore multiplicative constants, like I said, so you really could just ignore this entirely and then work from it through here. Ignore combination growth function. Oh, you can combine. So yes, if it's based off, so if there's 2 for loops, but they're not nested, so you have like one for loop after another, think about it as like the big O of the first for loop plus the big O of the second for loop, and then figure that combination out. So if the first for loop has a nested for loop inside of it, and that one's n squared, and the next one's n, that'd be n squared plus n, so it's just n squared. So even though there's 2 for loops, if it's all in one algorithm, the algorithm has a time complexity, big O time complexity of n squared. So yeah, all of this is just an estimate of the time requirement as a growth rate. Like I said, it's not you won't use this to find the exact amount of time it would take a program to run. That you'll get more into in like comp.org based upon cycle time and stuff, but that's not, I'm not going over that now. This is just an estimate of the growth rate based upon the number of elements, which is still very useful. You want low growth rates because theoretically your algorithm can be used, should be able to be used with data sets of size like 5 and data sets of size like 1 billion. Okay, so here we've got 2 for loops, they're not nested. And so right here, outside of for loop, it's O of 1. Right here, this has an O of n because it's val.length elements, I++, like going through each element. Here, there's 2 checks, so you might think of it as 2n. Here, there's another O of 1. And then here's an O of n, just 1 check, so it'd be like 1. So this would be 1 plus 2n plus 1 plus n. And so you could add it all together as 3n plus 2. And then you take the base element, which is the 3n, cut off the constant, big O n. This process keeps going. Count from the inside out is taking over everything. So here there's big O, there's O1, there's 2. This one goes through all the elements, val.length plus, so that's 2n. Here's another n outside of it, so nested for loops multiply together. And so this goes through all the elements again, so that'd be 2n squared. And then out here, there's an O of 1, so it'd be 2n squared plus 2, top lowest, 2n squared, cut the constant, n squared. I think we show a not add for loop here. Oh, no, right here. So this one, j equals I plus 1. That's kind of the thing where we saw with selection and insertion sort, where it doesn't check every element, but it only removes 1 every time. So it creates a sort of 0.5n relationship when you average it all out. So this would be 1, 2 times 0.5n. How would that work? Okay, I'm not going to worry about the O of 1 stuff. So 0.5n, and then that's just n, so it's 0.5n squared, short. Technically with the 2, it'd be just 1n, whatever. With all that together, it's still n squared. So don't be tricked by it saying int I equals j plus 1 and thinking, oh, that's not checking all the elements, so it's log. It's not, it's linear, n squared. Do we have anything that's log? Well, here's a log. We don't have to give the code for it. Okay, sure. Here's a log algorithm. So this one, we didn't give you the code, but it's just an algorithm. This would be like pseudocode. So it's binary search. And in here, it's saying, well, low is less than high. Mid equals low plus high divided by 2. So that's the cut in half point. It's saying get the middle element. And then depending on what the middle element's value is, it either assigns high to the middle element or low to the middle element. So that's where the cut in half occurs. And so anytime you cut out the chunk of the information that isn't just 1 at a time, or like it's not a constant at a time, it's based relative to the size, that's log. You would see that more commonly in like a for loop, where if the increment of the for loop wasn't just plus I plus plus or I minus minus, if it was like I times equals 2. If you had that, you couldn't start at 0. So yeah, with I times equals 2, that's jumping over a bunch of elements every single time. So that would be a log component. Or if the other way around, you had that I equals length, and then you had I divide equals 2. Anything where you're multiplying or dividing the amount of the information you're checking, cutting out more than just a constant at a time, you're good. So yeah, plus equals 2 would not be, that would still be linear, even though you're cutting out 2 elements at a time, not logarithmic. Yeah, here, this one's an example of 2 different data sets. So we have I equals 0, I is less than n, and then j equals 0, j is less than m. So the fact that there's 2 different data sets, you don't actually add them together like we discussed before. So it's just n plus n. And since it's n plus n, it's big O of n plus n. It's not just, none of these answers are even appropriate for what it is. So there's no like big O of n or big O of m, and you don't multiply them together definitely. The answer is O of n plus n. And then here, this one, I equals 0, I is less than n, I plus plus, for j equals n, j plus greater than I, j minus minus. So this is the same thing that we talked about before, where it's it's greater than I. It's checking less elements, but that's only changing by 1 every time. So this would be n squared. It'd be n times n. Yeah, right there. N squared. And this one, it says right here, O of n plus n. So you should definitely be able to recognize more complex things than we just discussed here. Like you might have something like n times n, an actual exam or something. So be able to read just any for loop and recognize if it's n squared, and maybe even n cubed if we felt like throwing one in there. Be able to look for logs through anything that's multiplying or dividing. Keep an eye out for that. But you still have to look at it holistically, because like I said, we like to trick you guys, so just have to be on the lookout. Okay, so now we covered everything with that. Any conceptual or programming questions about searching or sorting? Okay. Next up for today, we have project 4. I had some students in my last period asking some good questions. I'm going to go over that first. Oh yeah, here's my super basic. The question that I got was, the get next direction function that returns an int. So they're like, is that a length? What are we doing with that get next direction function here? Why is that returning an int? This function, so there's a bunch of functions that return ints. There's like int get x, get y, that returns a location based off of x, y coordinates. There's get num of neighbors, so that's like if you're at an intersection, how many things are around you, or if you're just in a hallway, there'd be 2 neighbors. Get half distance, that is definitely a distance. I couldn't tell you for the life of me what that's based off of. I think it might be pixels, but I'm not entirely sure. But just in general, it'll give you a good distance. You can mess around with it to find the exact numbers you want to use. Get direction, so that one is related to get next direction, which I'll cover in a second. Same with get reverse, those are kind of related. Get layer time and get vulnerable time are times. So I think those are in seconds or something, but just again, you can play around with it to see, it might be milliseconds or something. But the get next direction and anything that has to do with the direction, 0 to 3 are a direction for Pacman to go. So it'll actually change which way Pacman goes. So if in our little thing here, we hard code 0, so have it just return 0. 0 means go up. So if we do test agent visual with just hard code return 0, it's going to constantly be trying to go up. If it can't go up, it's going to continue the path that it was going. So you'll see that at the beginning, it won't just stand still as it tries to go up against the wall. But it starts out pointing left, and so it'll try to go left. But once it hits an up, it's going to try to go up. And since the direction it was originally going in was up, it's going to keep trying to go up. So that's what that is. And then I think it goes clockwise. So 1 is right, and then 2 is down, and 3 is left. But we'll just test it out real quick. But yeah, that integer value that those are giving, that's the direction itself. You don't use that as like a distance. That is the direction. So the get next direction function is super valuable. So yeah, 1 was right, and then that's going to continue the pattern. It's not going to be running wonky. 2 is down, 3 is left. Does that make sense to all y'all? It was a good question from a student who was confused, so hopefully that helps. The next thing I went over was just generally how to throw some stuff together. So there's down. I won't show left. But putting this all together, like let's just say you're testing out some basic stuff, because you should do that. The first thing you should do is run some super basic code. Like just run away from ghosts, run towards nearest power pill, run towards nearest pill. Just do single lines that do that. Because I'm going to write right now a single line that is run away from ghosts. So to run away from ghosts, some things we want to look at. Get next direction. That's going to be super important. You call get next direction on an actor. We're trying to get the next direction of Pac-Man. Pac-Man's the attacker, so we got to get the attacker. Get the attacker, you call that on a game object. So we have the game object right here. So to start, I'm going to do game dot get attacker dot get next direction. There we go. So that's the start. Next, you have to pick a node to go towards or away from. I want to go towards or away from the nearest ghost. To find the nearest of something, actors have get target actor. And so given a list of actors, find the closest or furthest. So we'll use that with a list of actors. So to use that, we have to use an actor interface. Same thing, gotta get Pac-Man again. So there's 2 elements in here. So first element, we gotta get the node of the nearest ghost. So we gotta call the get target actor function. We call that on Pac-Man. So game.get attacker get target actor. There we go. And here, the list of actors we want is the list of defenders. Defenders are actors. So I'm going to get the defenders. That you call in the game object. So game, and I know I'm doing it now. I don't think there's anything more complicated. We do game.get defenders. So that's a list of actors. And then here we want the closest. So that's true. I'm not looking at documentation, but just understand that it's true. And so this gets the closest actor. But this needs to be a location. So to get the location of an actor, you call .get location. There we go. And then here we want to run away from it, so I'm going to do false. So this super basic setup, this is all one line. You could break it up. You could break it up with like attacker, Pac-Man equals game.get attacker. And then just paste this everywhere you do game.get attacker. So that's what I'd be looking for in like your final submission is for stuff like that. But with this testing, you don't have to do that. Whatever makes sense to you. The whole point of testing is you try something out, and you're done with it. You just keep that in your memory banks of how to do that, and then you throw it out. So just now when you're working on future stuff, you know how to do this. And so this right here, it gets the attacker object, gets the next direction. So this whole thing is a node. And so the next direction from this node is getting a target actor that's closest to the attacker object. The list of actors is the list of defenders. We're saying get the closest one and then get the location of the closest one. And then this right here is running away from this node that we gave. So running this, test stage invisible. Our little Pac-Man will just be running away from the nearest ghost. And he actually doesn't do that bad, of all things considering, for the singular behavior. There are some singular behaviors that actually do really well. I'm not going to show you that. But this singular behavior doesn't do that bad. Like it stays alive for a while, gets some points. Now right here, for this kind of thing, you could be looking at this and thinking, man, I should do a check to see if the ghosts are vulnerable or not. That's something you can definitely do. And if they're vulnerable, you wouldn't even need to worry. Another thing was at the beginning, it was running away from ghosts, even though there was no ghost near it. Like right now, it's running away from this ghost, but it's not really even near it yet. So you should have some sort of check to see like how close the nearest ghost is. And if it's actually near you, then you can run away from it. But if it's not very close to you, you don't need to worry about it. But stuff like this, it's just basic behavior, seeing what it does, thinking about some improvements for it. That's the kind of thing we want you to do. Just simple stuff like that. Does everyone understand how this function works? Be able to recreate it with yourself with more things. Okay. And just last but not least, I'm going to do just going towards the nearest offender, just a suicidal Pac-Man. Why not? You can make Pac-Man do whatever you want. He'll be okay. He'll revive. Actually, I think this is based off of Mrs. Pac-Man, so that's the female. She'll be okay. I promise. She'll revive. Yeah. The ghost was running away. She's like, nope, come back. Okay. So obviously that is worse. You shouldn't be running towards the nearest ghost 24/7, but there you go. Oh, and then, so these base behaviors, obviously super important, but in your final thing, you should probably have something where there's multiple if, else, and maybe just an else if. There you go. Else. And so have multiple conditions like this. The first one being here being like your primary, like if this is happening, you need to do this, and then so on and so forth. So your first one might be like, if there's a ghost within whatever distance from you, you need to go in here, because running away from an invulnerable ghost or going towards a vulnerable ghost is like your number one priority. So that should be this if statement. So you can check to just see if there's a ghost close to you, and then inside of here you can see if it's vulnerable or not. If you just want this thing to be run away from nearby ghosts that are invulnerable, you could do two checks. You could do the distance check and a vulnerable check. So just check the distance to the nearest ghost and see if the nearest ghost is vulnerable. And if it's not vulnerable and it's near you, run away from it. And that'd be like your number one priority. Staying alive is what you want to prioritize. Whatever else you want to throw in the middle, be it go towards power pills, go towards whatever, you can have a bunch of also change there to decide your priority. And then finally, maybe a good last thing is like, if nothing else is true, if nothing immediate is going on, just go towards the nearest pill. So that kind of thing, which is like a basic behavior to get some points with that. So with that, that's basically all I really want to talk about. Are there any questions about the Pac-Man project? It's your big class project. So the last class project was implementing a class. This is your big one about using the class. Both of them you need to be comfortable with. Okay. If there's nothing, the rest of my lab is office hours really. Like if you have any questions, I'm here for it. Feel free to just work on the project, and I can answer any questions as you go through. But this is an optional lab anyway, so you're free to go whenever. But I'm now saying I'm done with content. I'm